everyone to the HPL seminar. It's nice to see everyone. Today we'll be hearing from Brian Yu. Brian is currently a master's student with Walter Herzog, and he hopes to complete his degree at the end of 2022. Prior to his master's, Brian completed his bachelor's in kinesiology at the University of Alberta in 2014. Since 2014, Brian has also been a strength and conditioning coach at the Canadian Sport Institute, and he has worked with the speed skating program and the men's Paralympic hockey team. He has also worked with the speed skating team in China. Brian's research interests include understanding speed skating performance and training from a muscle physiology and mechanics perspective. A fun fact about Brian is he almost quit his undergrad twice. Once to become a truck driver and another time to become a professional StarCraft 2 player, but he is glad that he stayed in school. As a reminder, I will first turn it over to Brian for his presentation, and then we'll have a question and answer period to follow. And at that time, I'll remind everyone how to submit a question. With that, Brian, you're welcome to start sharing your screen when you're ready, and we look forward to your presentation.
Thank you, Emily. So the title of my presentation is called Moment-Angle Relationship in Trained Speed Skaters and the Operational Fascicle Length During the Turntable Exercise. Long track speed skating has been in the Olympics since 1924. The events range from a 33-second 500-meter race to upwards of 13 minutes. For a Canadian exercise professional, it's important to understand the sport of speed skating because it is a high priority sport with its high medal winning potential. So for those who have never seen speed skating, show you guys a clip. Just pay attention to their unique skating position. If you ask any speed skater or speed skating coach, what defines as good skating technique? 9 times out of 10, they're going to tell you that you have to skate low. And that makes sense because skating low is associated with better speed skating performance. And it does so by the following reasons. Number one, wind resistance is a major resistance in speed skating performance. So they counter this by wearing special bodysuits as well as just simply skating lower. By having a lower starting skating position, you give yourself more distance and more time to apply muscular force into the ice. And studies have found that the low starting position also helps you apply force more efficiently in the lateral direction. When we're talking about skating low, in both the literature setting as well as in training, the knee angle is often the topic of interest. When we're referring to this knee angle, we typically are talking about the angle during the gliding phase and the pre-extension phase of speed skating. So when the knee angle is at a quasi-isometric state. The normative knee angle in skating is between 70 to 90 degree knee flexion. Now I'll take this moment to note that for this presentation, we're going to refer full knee extension as 0 degree. So the greater the knee flexion angle, the deeper and the lower the skaters are skating. Just looking at the knee angle alone, when comparing a cohort of skaters of the same age group, studies have found that the faster half of the group skates typically 5 to 10 degrees lower than the slower half. Similarly, the senior and elite skaters also skate around 10 degrees lower than their junior counterpart. When comparing the first lap of the race to the very end of the race, we typically will see a 10 to 15 degree knee angle difference between the two time points. Now this relationship between knee angle and performance is further supported by a modeling study which showed a 9-degree difference in the knee angle could lead to a 1 second per lap difference in skating performance. To put that to perspective, this is the result from the previous Olympic Games. We can see that what separated gold and silver was merely 400th of a second. So you can bet that even 1 degree of difference in knee angle is worth fighting for. In order to skate lower and be stronger in this low skating position, speed skaters undergo high volume and intensity of positional specific training, such as skating on the ice and these technical dryland exercises that are shown here. Above all the dryland exercises, the turntable exercise that's shown here is probably the most iconic exercise and most commonly seen around the speed skating community because it mimics the curve skating portion of speed skating, which is said to be more technical and more force demanding. At this point, I'll be asking myself, does training low actually make you stronger in the low position? If so, what are the physiological mechanisms behind such adaptation? In order to talk about that, we first need to talk about the force-length relationship, which explains the length dependency of maximal force production in skeletal muscles. The graph on the right here represents a force to sarcomere length relationship of a frog muscle. We can see that the maximal force producing capability is directly related to the length of the sarcomere. On a higher level, using ultrasonography, we can get a similar relationship by looking at the muscular force to the fascicle length. On an even higher level, we can see a similar relationship between the joint moment and the resulting joint angle. And this is what we call a torque angle relationship. This is commonly used in human performance testing because of its ease of usage. And the current literature have shown that between athletes of different sports, we can see distinctive differences in the moment angle relationship in many different joints. And that's presumably due to the specific sporting demand. In untrained participants, studies have also shown that the moment angle relationship, specifically the optimal knee angle, can shift towards the training angle at an isometric training under an isometric training program. So on the graph here, we see the optimal knee angle on the y-axis. On the x-axis, we have pre-training, week 5 and week 8. And after conducting isometric training at the 90-degree knee angle, participants drastically shifted their optimal knee angle towards the trained angle. Lastly, it seems like the fascicle length used during training seems to also influence the torque angle relationship. So in this graph here, the participants trained at 25-degree hip abduction at a submaximal state. So the fascicle length that used would be slightly longer than the maximal state at this knee angle. And when after 4 weeks of training, they tested at maximal effort, they found the torque increase drastically significantly improved at an angle that's corresponding to a longer fascicle length. So my project is driven by 3 rationales. Number one, that it is essential for us coaches to evaluate what matters. So we need to have a reliable and valid way to measure what the impact of our training program on our skaters' ability to skate low. Second, we commonly assume that speed skaters are just stronger in the low position compared to non-skaters, but we don't really have any evidence to support that. And lastly, in order to drive training innovation, it will be very interesting to understand the operational fascicle length during actual speed skating. And we think we can do that by studying the skating specific dryland exercise. With each of our rationale, we develop a research question. The first question, we're curious about if trained speed skaters can alter their torque angle relationship after only 3 months of sport-specific training. We also wanted to compare the torque angle profiles between our speed skaters and non-speed skating physically active control subjects. And lastly, we're curious about what the operational fascicle length of the vastus lateralis during the turntable exercise, which was shown earlier in the background. To answer our questions, we must go through how we're planning on measuring. So first, we recruited 16 speed skaters from the Calgary Olympic Oval program. The average training age of these skaters were all above 5 years. They must have been injury-free 3 months prior to the testing dates, and all reported over 90% of training compliance. At this point of my research, we've recruited 8 control subjects. And it's important to note that for the study, we're only going to look at the left knee because it is subjected to the greatest knee flexion. And we're only going to look at the vastus lateralis for its size in terms of the knee extensor muscle group. We recruited our participants back in May when they were relatively detrained following a off-season as well as COVID complications. In this baseline testing, we measured their torque angle relationship. After the baseline, participants went on for about 3 to 4 months of summer training. And here's an example of what their weekly training consists of. And then between August and September, we brought back the same participants and performed a post-training torque angle test. This time only the speed skaters. In addition, we conducted the turntable operational fascicle length test right after the torque angle test. For the torque angle test, we used a standard dynamometer. We strapped on an ultrasound probe and EMG probes on the participants' vastus lateralis. They conducted maximal voluntary isometric knee extensions at 9 different angles in a randomized order. Then we collected knee extension torque, knee angle, fascicle length, and the relative EMG from this study. Here's a video to show you guys an example of what the test looks like and how torque kind of is produced. So we're going to watch it again. This time, pay attention to the change in knee angle during this test. Due to soft tissue compression and equipment compression, we've realized that the resulting knee angle during isometric knee extension actually changes. So we decided to use 2D kinematics to measure the actual knee angle during maximal contraction. The third outcome was fascicle length using ultrasound images. Before we get into it, let's talk about how to read a ultrasound image. So the ultrasound probe is attached to the mid-belly of the vastus lateralis, shown on the schematic diagram here. The top of the image represents the skin, and the ultrasound probe from here will give us a longitudinal view of the muscle belly. The two thick white lines are the epineurosis, and all the straight lines in the middle here are our muscle fascicles. So during contraction, we can see that the fascicle shortens as torque builds up towards a plateau, and it lengthens once again once the muscle is relaxed. From here, we take the ultrasound image during peak torque production, and using the software ImageJ, we were able to measure the length of the fascicle, like so. So that explains our first test, the torque angle test. Now onto the turntable test. I'm going to show you guys a cool video of what the test looks like. So as we saw, the test is conducted on an instrumented treadmill. The participants wore the exact same setup with an additional electrogoniometer on their knee. They performed maximal effort turntable on the treadmill at the same velocity across all participants. The outcomes for this test was the knee angle from the goniometer this time, fascicle length, and the EMG. So I'll take this moment to show you a cool slow-mo video of the fascicle length changes during this dry land exercise. We decided to examine the fascicle length at 3 distinct time points of interest. Number one, using 2D video kinematics, when the foot makes complete contact, we label this as initial contact, and we get the knee angle and the fascicle length at this point. During the mid stance, when EMG peaks, we take into account of electromechanical delay by 100 milliseconds, and we use that as our peak EMG state. And lastly, we have our takeoff when the foot loses complete contact with the treadmill belt. So these are 3 time points of interest. So that summarizes our research method. On to the discussion and results. We're going to be presenting our results and discussion one by one in relation to our research questions. So first, we're going to look at the torque angle relationship in trained speed skaters, comparing baseline to 3 months post-training. For the results, we're taking the peak torque at each knee angle, graphing it against the actual knee angle during peak contraction. In order to compare participants across the board, we normalize our torque values, and we're able to get a torque angle relationship on all 16 speed skating participants. Here we have the relative torque in the y-axis and knee angle in the x-axis. Once again, 0 degree being full knee extension. And we can see that the optimal knee angle in our baseline testing was around 67 degree knee flexion. After 3 months of training, this is our post-training test in the red dots. We can see that there's virtually no difference across the board at any given knee angle, and the peak and the optimal knee angle is essentially the same as well. So to dive into it a little bit deeper, we're going to switch gear from looking at the knee angle to looking at the fascicle length during these isometric contractions. And when plotting a relative torque on the y and fascicle length on the x-axis, we saw the same result. So no differences across the board, with our optimal fascicle length being about 2 millimeters in difference. So that answers our first question, whether or not trained speed skaters can alter their torque angle relationship after 3 months of training. So we saw no differences in either the torque angle relationship or the torque length relationship. Now, one reason could be that the analysis method we're using so far is relatively simple. So perhaps a more complex method of looking at the polynomial of the curve could give us different results. Because the training age of our participants were all quite high, so perhaps if 3 months of training was not long enough and sufficient enough to induce any changes to their torque angle profiles. The time of the competition when we collected these results were still quite early in terms of the competition season. So perhaps as they get into their competition season, as they peak towards major competitions, we could maybe expect some changes in their torque angle profiles. And lastly, there's a chance that based on their training intensity and training angles, the predominant fascicle length in training was not conducive enough to make any changes to their torque angle profiles. So on to our question number 2, wherein we're interested in comparing speed skaters to non-skating control subjects. We conducted the same test in the dynamometer, and here is a graph of the results. Once again, y-axis is the relative torque, and knee angle is labeled on the x-axis. We saw no difference in the optimal knee angle between our control and baseline speed skating results. However, when we look on the right side of the graph, we can start to see some distinct differences towards the deeper knee flexion angles. So taking away our standard deviation for a closer look, we were able to find significant differences in their relative torque from the 88 degrees to 113 degree knee flexion. Unfortunately, we do not have any fascicle length results for us to dive into this change a little bit deeper. In answering question 2, we found significant difference in the deeper knee flexion position between speed skaters and our non-skating control subjects, with our speed skaters being significantly stronger in the deep position. Now, this could be evidence to support that there was indeed some chronic adaptation from their sport demand, from their skating position and their daily training environment to induce such change. Some studies have also shown that there could be a neuromuscular activation bias upon angle-specific training. And in combination, there could be a actual fascicle length differences between our skaters and control subjects. Our last question, we're curious about the operational fascicle length during our turntable exercise. In order to put our operational fascicle length in perspective, we're going to overlay the fascicle length during the turntable test on this individual's torque to fascicle length profile. And I apologize that we only have one participant's results analyzed at this moment. So during initial contact, when the knee angle is the deepest, we saw a long fascicle length at 110 millimeters. During peak EMG, fascicle length shortened to 95 millimeters. And at takeoff, when the knee angle is close to full knee extension, our fascicle length shortened to 77 millimeters. Now, it's interesting to note that the physiological optimal fascicle length that was obtained during the torque angle test was only 2 millimeters different than the fascicle length that we found during peak EMG. So we're curious about if a similar trend could be seen when we compare the knee angles during this test. And here are the results. We can see that the knee angle, they entered the movement at around 120 degree knee flexion and finished near 30 degree knee flexion. However, when comparing the optimal knee angle, once again obtained from the torque angle test, we found a 20 degree difference than when peak EMG occurred during the turntable movement. So for our third question, we found that the operational fascicle length of vastus lateralis encompasses both the ascending limb and the descending limb of the torque length profile of this one participant. Specifically with the fascicle length at peak EMG occurring near the optimal fascicle length. I understand there's only one participant, but if we continue to see such trend, then it'll be interesting to start speculating about a possible cause and effect of why there is such overlap at this optimal fascicle length time point. We saw a huge knee angle differences when comparing to our fascicle length differences. And at this point, it could be interesting to speculate that perhaps fascicle length is indeed a bigger driver than the knee angle used during training. giving our Fascicle length the gold medal by a smidge. In summary, we found no differences after 3 months of sport training in our trained speed skaters' torque angle relationship. We saw a significant difference in the deep knee flexion angles between our skaters and control subjects. And lastly, the Fascicle length used during the turntable exercise encompasses both the ascending limb to the descending limb. Some of the major limitations of our study was that we had no control over their summer training program. So we could not implement any joint angle specific training or anything to target such changes. We also did not have control over the participants' fatigue level and recovery level coming into these tests. We had no baseline testing in terms of speed skating performance that we can compare with our post-training test. We recognize that knee angle is not the only performance metric in speed skating. There's technique, there's the hip joint, there's the ankle joint, and there are many other factors that influences skating performance. And lastly, fasciculus lateralis only represents about 33% of the muscle mass in the knee extensor group. And we recognize that some of the other knee extensor muscles could have an entirely different force length profile compared to our fasciculus lateralis. With that said, I want to thank my supervisor, my committees, and all the people who have helped me along the way. Thank you very much.
Thank you, Brian. That was a great talk. I would like to, at this time, ask everyone in the audience that if you're comfortable, if you please be willing to turn on your camera to allow for a better discussion time. The floor is now open for questions to Brian. To ask a question, you can use the raised hand function by clicking on reactions located on the lower part of your Zoom screen. Alternatively, if you are unable to raise your hand, you may type your question in the chat box and I will read your question out loud. And I see that Amin has a question, so I'll let him start things off. Amin, please ask your question.
Thank you, Brian, for your presentation. In the ultrasound images, I could identify several fascicles, muscle fascicles. So I was wondering which one did you select to do the measurement?
That's a good question. Do you mind if I share a video with you guys real quick? Give me a sec here. Okay. So when we were deciding which fascicle to choose, that becomes our primary source of error. So to minimize this error, we decided to draw a red dot in the center of every ultrasound image and use the fascicle that's associated with the center dot across the board. So that was our approach to minimize this selection bias in terms of fascicles.
Did you try to measure different fascicle lengths out of one image frame to study the variation of fascicle lengths that you have?
Unfortunately, I have not done that just yet. I am in the process of measuring all of my fascicle length data the second time to get an idea of my personal reliability.
Because in the first measurement, you may measure fascicle length, and then in the second measurement, you may measure fascicle length of like another fascicle. So you're comparing two different fascicles, right? So that might be like a source of error.
Yeah, I think that would be an interesting one to see. So you're saying comparing multiple fascicles within the same image and see what kind of variability there are. That would be an interesting thing to do.
Yeah, and when you want to measure the change in fascicle length, you're going to make sure you're tracking a single fascicle, right?
Yes.
That's my point. Yeah. Thank you.
No, I agree. Thank you.
I think you guys raised your hand at the same time. So Art, you're showing up first on my screen if you'd like to ask your question.
Sure. It looks like most of your results were in terms of relative torque angle relationships, and I'm just wondering if anything happened in the absolute, in the sense that, I could imagine, what if somebody was training and then they increased their strength overall by 10%? Does that mean that their relative curve looks exactly the same, but they are stronger and perhaps even faster?
That's a good question. I forgot to mention that the absolute torque in the speed skaters before and after had no difference at all as well. That's why we just presented the relative torque. However, we were able to see some individual differences in their absolute torque production. So let me see if I can find any graphs for you. Okay, got it. One sec. So here we have results of two different participants with their absolute torque to their knee angle. The green is our baseline again, and the red is post-training. So we chose these two because one participant showed a interesting right shift of their torque angle profile, while the participant on the right here actually shifted his optimal knee angle towards the more shallow knee position.
And is that a repeatable measurement?
I'm still in the process of doing my repeatability for the torque angle test, but from the literature on reliability of this test, we can expect I think it's around 8% of difference of kind of randomized variability.
And so I guess what the results lead me to think is, I wonder, so when they're training, I mean, I presume if they're training all summer that they're improving in some aspect, but maybe strength is not their primary focus. Maybe they're more interested in other things.
That was one of my major questions as well. This is why we, in one of my slides, we talked about the time of the season. One thing I did notice was that in our post-training testing, the skaters came in mostly all relatively fatigued compared to their baseline state. And that was a huge limitation of our study, because due to their busy training schedule, we couldn't ask them to taper or rest prior to coming into this test. So I think that would definitely influence their ability to express maximal force during the test.
Mm-hmm. Well, one thing I would suggest might be helpful is, since you have measurements of them on the instrumented treadmill, you basically have an ability to measure I guess I would call it a sport-specific power. So what power are they producing, and maybe for how long, or what's the peak power they can produce. But those are measurements that you can do that look pretty specific, right? So they are, they're in that position, and then it might be a good simulation of what they're experiencing in real life.
I absolutely agree. That's our next step. I'm really curious about what their ground reaction force curve looks like in this dryland movement, and we can compare it to pressure insoles that's being recorded during actual speed skating. And we can see if there's similarity in how they produce force and all the other cool stuff you just mentioned. So,
yeah,
pretty exciting.
Thanks.
Thank you.
Robert, please go ahead.
Brian, I congratulate you for attempting this. I know this sort of work is difficult to do, but I'm not sure why you chose the vastus. Is that my guess is it's the easiest one to put the sun micrometer onto, or the measured with ultrasound. But I'm not sure what your expectation was. If you were thinking that it was going to operate over a longer length, were you thinking that the muscle might lay down more sarcomeres in series in order to be, sitting closer to the peak and therefore being able to operate over longer lengths? But if you were to choose, looking at the skating and bent over like that, if I was to choose it, not because of the easiest muscle to do it, but which muscle may have to go through a longer excursion, I'm wondering if gluteus muscle has to, I don't know how possible it is to put a ultrasound on gluteus muscle, but I'm wondering if it would show more likely an increased range of lengths to operate over, and therefore one where you might suspect that speed skaters have to lay down more sarcomeres in series to get a flatter curve. What are your thoughts on those?
I absolutely agree. If in the perfect world, I would have measured the glute muscle for a couple reasons. The glute during the curve skating portion of is actually undergoes the most amount of force production and the greatest range, like you mentioned. And there is a study out there that compares inline skaters to non-skaters, and they found exactly what you said, that skaters' abduction range of strength was significantly different compared to controls.
Yeah.
So to build up on that, I guess we chose vastus lateralis for exactly what you said. It's one of the most studied muscle. It's the easiest to measure. And I'm also just very curious about and also how it's related to the important knee angle. And we're curious about if the fascicle length used during this dryland exercise can be learned, and we can kind of shift our paradigm from training angle specific to perhaps experimenting with some training that are fascicle length specific. So I'm going like really far out there right now, but that is the long-term hope.
Right. The measurement of the fascicle length, my guess is to get perpendicular to the fascicle to make your measurement is what you hope for. But watching some of those videos, it looked to me as if it was perhaps rotating. And so how much error do you think there might be? And you must have some sort of feel for it, that it's the fascicle is actually rotated slightly out of your plane of measurement. And so you're not actually measuring the true length, you're getting an estimate of it. How big do you think that error could be? Enough to bother these things?
I actually don't know what the typical error of measurement would be. So I measure every fascicle image 3 times using the same method, and my standard deviation is around 3 to 4 millimeters. So just within myself, that's quite a bit of error. And for fascicle images that are outside of our frame, is this what you were referring to when it's kind of rotated and we can't
Yes.
see the entire fascicle?
Because what you're looking at, in fact, is not the fascicle. I think what you're looking at is the connective tissue between fascicles.
Yeah, so I'm not super well read on this. I believe these orientation of the connective tissue represents the fascicle length, but correct me if I'm wrong.
But it could rotate this way into, if you could find a blemish on the skin that you could put your little red marker on, and a blemish on the other end, that would help you to see if you were still in the same spot. But you've got young people, unlike old people who have lots of blemishes, you have young people who are pure.
That's a good point. That's one thing we did not do, was to place a reference marker like a copper wire, like what Mike has done in the past. So unfortunately, we have to recognize that as another limitation. But
Yeah.
Thank you for that point.
Anyway, I know it's a very difficult study, so I congratulate you for doing it.
I appreciate it.
Matt, please go ahead.
Hi, Matt.
Hey, Brian. First of all, just a little feedback. I thought you did a really good job presenting there and just explaining what you did. It was easy to listen to, and there's so many results and so much stuff going on. Is that to be able to do that and make it concise, I think was, I'm sure it was a challenge, but you did a good job there. So nice work on that.
Thank you very much.
And I really want to say as well too, some feedback that I think, even though it's hard, and even though these things are difficult measurements by virtue of the human subjects doing complex movements, I do think it's important research. So good job. I guess the one question I always have when you present data like that and you've got elite athletes and I noticed, like, for example, your torque joint angle relationship, you showed some error bars and things look pretty tight. And when you eyeball it, it almost looks like it's kind of the opposite of what you think, even though I know it's not statistically different. It looked like, maybe there was this thing where it seemed like after training, it almost favored that they were making higher torque at the shorter joint angles. It was like it kind of like went up and then it intersected and then it looked really no different. And then I noticed on the other figures, it was sort of consistent as well. Like you saw that same sort of pattern with the fascicle length measurements, but there were no error bars, so it was impossible to tell how variable it was. And I guess, it's kind of counterintuitive that I know it's not statistically different, but it makes you wonder, like, are there people inside the group in these 16 speed skaters who may have responded one way very excessively and others who maybe did not change? And is there anything on the individual level where it would be worth it to examine to see how each person changed, rather than using sort of a collapsed average for the group, just knowing that it's individual, right? It's individual things. Any comments on that, Brian?
Yeah, I think that's a really good idea, because when we're dealing with high-level athletes, we are dealing with the individual. And that is our plan going forward, is to examine. I'm still kind of working out how to separate the group of athletes. Perhaps I'll look at people who are more sprint orientated versus people who are more long distance orientated, or we can compare results in their skating performance. But I think that'll be really interesting to dive into the individual shift in this moment angle or even torque length profile of these individuals, and
I think it's
assess.
I think it's a great idea, just only because, having been around that sport for a long time, what I know is that some skaters seem to be highly resistant to changing that fundamental body position. And so even though the fact that they did sport specific training, whether they did it with the intention to actually make a change and they did like, that's another question, right? Altogether. So I wonder if there's a way you can tease that out a little bit, you know, either like just eyeball preferred joint angles on ice in terms of how they skate, or something that might help you inform there a little bit on the n=1 level.
That's a really good idea. Maybe I'll reach out to you another day, and I can ask for more of your thoughts on this.
Yeah, nice job though, Brian.
Thank you.
Mike, please go ahead.
Hey, Brian, good presentation. I just had a quick question about the training. I know you said you didn't have control over it, but were the athletes doing any of the specific training at like the lower knee angles? And to what extent were they doing that a lot of the time, a little bit of the time, or like none at all? I'm just curious.
Yeah, give me 1 sec. I'll pull out this. So all the skaters in the program, they train as a group, or train as like 2-3 different groups with a designated coach. And this is a typical amount of training they would do in 1 week. So just the on-ice training alone, we would consider angle specific. So that'll be 4 times a week. And the technical dry land, which would be consists of exercises that I showed in the background, which once again pushes the skaters in this low position. The issue here becomes similar, relating to what Matt was saying, is that at this training age, a lot of the skaters kind of just default to a set pattern of movement. They don't try to go any lower. They don't try to push their limit because it becomes too difficult. So perhaps when they were actually conducting the skating and dryland training, they were not pushing to skate lower. Hence why we saw no shift in their optimal joint angle.
Fair enough, makes sense.
I have a question, Brian. You motivated at the start of your talk that the athletes with deeper knee flexion had better performance, but then your torque knee angle results were U-shaped. So does that mean that the athletes could also be too flex, such that they start having a decline in performance eventually?
That's something I've asked speed skating coaches before, and then the answer is yes, they can skate too low and actually cause their technique to fall apart and cause them to fatigue too early. And that's reflected in when you compare a sprint event to a long distance event, that sprinters would typically skate much lower compared to the long distance skaters. And that's because, sure, it puts you in a better mechanical position to apply force, but you also fatigue out even faster. And also another conflicting variable in speed skating performance is that the lower you skate, the more blood flow restriction you're subjected to in your legs, and that could lead to faster fatigue. So there's always a balance.
That's interesting. And I have one more question too. So if fascicle length ends up being a more appropriate metric to try to tune for performance, what does that look like in a training environment? Like, do all these coaches have to buy an ultrasound probe?
Nope. I'm so glad you asked that. I've been like playing in my head how to train such characteristics. So we know that fascicle length lengthens when you bend the knee. So the deeper you are, the longer fascicle length gets, but also shortens the harder you contract. So I would design an exercise that puts you in a lower knee angle than what you typically skate at and perform near maximal or maximal isometric contractions, where we focus on generating force quickly and generate a high amount of force in this below average position knee angle. And that way, hopefully our resulting fascicle length will be kind of crossing over and similar to what they use in skating.
That's very interesting. Thank you. Walter, would you please like to ask your questions?
Maybe Mike goes first because I have a ton of questions and I'm worried you're going to run out of time if I start talking. So Mike, why don't you go first?
Oh. Can you hear me, Brian?
Yes.
Cool. My first one is this a phenomenon that's due to the invention of the clap skate? So the ability to lengthen the stride because the skate results in changes in the muscle architecture and then the second one that kind of builds on that is, do short track speed skaters use clap skates? And if not, do they see these same changes?
So answer your first question, I don't think this is a phenomenon due to clap skate, because when the clap skate was introduced, it was to address the ankle joint moment. And so when comparing traditional skate and clap skate, the only difference they found in kinematics was in the ankle, which resulting to they're able to extend they're able to plantar flex more with clap skates. And in short track, they do not use the clap skate. However, I think this study would be amazing to do in short track speed skaters because they actually skate in an even lower position. It's a thing between short trackers and long trackers. They are always battling each other on who's training better. And short trackers' badge of honor is usually they train lower, they skate lower, they're more resilient in the low position. So it could be a really cool follow-up study.
Interesting. Well, thank you. Nice presentation.
Thank you very much. All right, Walter, it's all yours.
Multiple questions, some very small and some more conceptual. Let me start with a more conceptual one. I wasn't quite sure how you defined optimal fascicle lengths because you bring in that term. How did you define optimal fascicle lengths?
The optimal fascicle length in this presentation was simply the fascicle length during the highest amount of torque production in the moment angle test. So the optimal fascicle length would be corresponding to the optimal knee angle. Yeah,
that's exactly what I thought you probably did. And then the question becomes, when you then do the functional testing, then your optimal fascicle length is close to some other value, I think peak EMG, if I remember correctly.
Yes, sir. Yeah.
Whereas your joint angle is far away, which then means, despite the fact that optimal fascicle length and optimal knee angle are kind of the same, in that movement they are dissociated, which is normal because you have different, because your fascicle length is determined by how long the muscle is and how much force you exert. But what puzzled me is that your joint angle was to the left, so that means you were about 20 degrees lower.
Yep.
That means longer muscle lengths, which means in order for the fascicle to be at optimal length, you would need to exert more force to be at optimal fascicle length at a longer muscle length. And I'm trying to figure out, because you're doing an eccentric contraction in your skating and you did an isometric contraction when you did your torque angle relationship, and I would have expected that the force would be higher in the isometric contraction and would be lower in the shortening contraction. And therefore, I cannot reconcile, because now I have a longer muscle length and what I thought would be less force. So how can the optimal length be there, but your knee joint angle is far away? Do you know the dilemma that I have?
Yeah, I do. Especially So the skater's in a deeper knee position, and the EMG compared to the torque, the EMG during the turntable test is about 70% to the peak EMG during the torque angle test. So that would indicate as well that they're activating at a lower state. So the fascicle length should be even longer, not short to the optimal.
Yeah. Anyway, it's an interesting thing and something to look at. The simpler question is, I wasn't quite sure why you would choose peak EMG, for making the specific comparisons, because I always find peak EMG is somewhat arbitrary, whereas let's say peak force or something like that might be a more consistent measure.
I agree. Twofold answer. First is it was purely due to the ease of defining this point without eyeballing throughout the kinematic analysis, and I wanted to present something right away for this presentation. And two, when we look at the EMG, instead of the random fluctuation during such that we see during the torque angle test, I found the EMG to be relatively predictable and follows a pretty good trend throughout the turntable test, such as here.
Mm-hmm.
So
okay. Yeah. No, I mean, that's exactly what I was looking for. If you checked it and you find that it's actually relatively consistent relative to the force or where it occurs in the step cycle, then maybe they have this activation that goes up and down and it's very consistent. So it might be very good value. So that could actually be.
Yeah, I think the next step can be look at the force value and further define the stride too.
Mm-hmm. Yeah. The other thing I was wondering is, when you showed the torque angle relationship, you showed error bars in the vertical direction, which makes sense. Not everybody has the same relative force, but you didn't show any error bars in the horizontal direction. And I would assume, since you took the angles not from the cybex, but once they had made once their knee joint angle changed slightly, I would assume that change in joint angle would not have been the same for everybody. And I would have expected a variation in the horizontal axis as well. Did you just not show that, or was there very little variation that was not apparent?
The variation was about 7 to 8 degrees both ways.
Okay.
And I didn't show it because I didn't know how to do it on Excel. So that's coding problems
good enough,
in the future.
Good enough. There is a variation there. That's all I want to know. We can figure out Excel, how that works. Yeah. And the other thing I was wondering was, so let's assume your results are correct. Okay, your results are correct, and you have a very similar relative force-length relationship on the ascending limb and the plateau between the skaters and the non-skaters. And then you have more force on the descending limb at the long muscle lengths, at the deep angles. How do you explain that?
I think there could be a combination of two reasons. One is the ability to essentially muscle activation. In some studies, they have found that the shift in torque angle relationship after angle specific training, that the EMG output at those towards the trained angle was significantly improved compared to subjects who trained at a different angle. And I got some subjective from conversation with the skaters was that when they're in the deeper knee angle, asking them about how they feel during the contraction or after the contraction, most of them preferred the deeper knee angle. They were, oh, that felt really good. That felt like pretty solid. As opposed to the control subjects, they just flat out would tell me, oh, that sucked. That was horrible. I feel like I had room to contract, but I couldn't do any more. So perhaps further looking at EMG can give us more answer.
Yeah, so that was the question. So you have not looked at the relative EMG yet in the various contractions and whether or not they...
Not in the control yet.
Okay, yeah. And then another question that I had is, I don't know about speed skaters, I was a track and field athlete, but you trained for very specific things at various parts during the season. So like in the off season, like which is summer for the speed skaters, which was winter for track and field, as a middle distance runner, you do these long endurance runs, you're not worried about speed, you're not worried about this, you're just worried about building up aerobic capacity as much as you can, or the strengths people, the shot putters, in the off season, they would lift the weights like crazy and try to get basic strengths as much as possible, not worry so much about the quick strengths, the speed and the power and that type of thing. So what do speed skaters do in the off season, like in the summer? So what's their primary goal that they want to achieve?
Their focus in the summer would be weight training focused. So maximal force, maximal rate of force development, as well as technical dry land. So working on technique, both on the ice and off the ice, using those specific exercises.
So would you assume that they do more exercising, including the skating, that they do more exercising in deep squatted position in the off season or in the on season?
The athletes I tested, I cannot speak too much about, but when I was working with those skating group and with Team China, I would say we do more volume in the low position in the off season. So we'll literally be doing technical dry land for 2 hours straight. And that's still the case in some selected group on the Canadian national team.
And then just a last little thing, more a remark, when you have these beautiful force lengths or torque angle relationships, I think one of the things you should do is kind of approximate these curves with a smooth function and then determine where on that function the peak occurs, because otherwise you have to rely on these very discrete fascicle lengths and angles that you measured. And it seems to me, some that come up slowly and then go down quickly and there, if you approximate that and kind of try to estimate where the actual peak might have been, might be quite a bit different.
I agree. I think that's our analysis limitation. Right now it's too simple, and I would definitely do what you are suggesting.
Yeah, great. Thanks a lot.
Thank you, Walter.
Are there any remaining questions for Brian?
Maybe a quick one. Have you already looked at, I might have missed that, have you already looked at fascicle lengths in your control group and fascicle lengths in your, no, okay. Yeah. What would you expect?
I don't know. I think they would be shorter. That's my hunch.
Shorter in who?
In the control subjects.
Compared to the speed skaters?
Yes.
Yeah. I think I would expect that as well, potentially. Got to be careful because, different sizes, people have different lengths, so you might have to normalize that somehow to a femur length or something like that, but yeah.
Okay, we can do that.
Yeah.
Are there any remaining questions? Great. Well, thank you again to our speaker, Brian, for presenting today, and thank you all for attending. Just as a reminder, there will be no HPL seminar next week because of the university holiday. So I will see everyone in 2 weeks for our HPL seminar then, and thank you all for signing on.